Good evening. We are Group 3, and today we will gonna be discussing the proposal of the substation scheme design for Bus 7 of the 12 bus system from Project 1 and Project 2. So, next, our objectives is to determine the appropriate substation scheme considering its function in the grid and other considerations, and explain the reason for choosing a particular substation scheme. Then provide the equipment specification for each of the major components of the assigned substation. There is a need to perform short circuit analysis to guide you in specifications of the equipment. Next is draw the single line diagram showing the major equipment in the assigned substation considering the scheme selected. Label each equipment using standard symbols, ANSI or IEC. Include the required metering equipment in the diagram and their specifications. Then, using the same single line diagram, draw the protection diagram of the substation assigned to your group. Next. So we have here types of common substations. So we have radial bus, sectionalized radial bus, main and transfer bus, single breaker double bus, ring bus, 1/2 breaker, breaker and 1/2, then double breaker double bus. So we will gonna analyze this types of common substations, and we will be choosing from the 8 types, we will be choosing only one. So next. So here is our substation scheme. So the group was tasked to assign a recommended bus scheme for bus 7 from the 12 bus system. So each part in the power system will be the same values from the base case model, which came from coursework 1. So an electric system facility with high voltage is called a substation. It is employed to switch circuits or lines, equipment, and generators. It can also be used to convert alternating current to direct current or direct current to alternating current, as well as to change AC voltages from one level to another. Next. So we have our classifications of bus types. So there are 4 types, which is the generating substation, step-up transmission substation, switching transmission substation, and the step-down distribution substation. So first is the generating station substations. So generator substations are located at the site of the power generating stations and provide the connection to the transmission system. Then the switching transmission substation, a substation that does not have power transformers and cannot switch the system voltage from one level to another, is called a switching station. Typically, switching stations run at transmission or sub-transmission voltage levels. So next is the step-up transmission substation. So a step-up transmission substation boosts the voltage for transmission to remote locations by using a sizable power transformer to receive electricity from a nearby generating facility. Then electricity is distributed to one or more transmission lines via a transmission bus. Then for step-down distribution substation, a distribution substation's main responsibility is to distribute step-down power. So these voltages are meant for end users, such as residential and commercial structures. Then the distribution substation also contains a few characteristics that makes it easier to use and improve safety. So the assigned bus in our group is bus 7. So in the Philippine context, the high voltage system class is 230 kilovolts. We may categorize it as a high voltage substation because According to standard categorization, it belongs to the high voltage system class. So transmission substations typically operate at high voltage, 69 kilovolts to 345 kilovolts. Since this project is connecting segments of the utility system transmission network without involving voltage level transformation, it has chosen to treat the assigned substation as a transmission switching substation. So here are classification of bus configurations. So from the figure above, according to the bus configurations, certain bus layouts in the list of standard or popular bus configurations are typically disregarded when considering them for a particular substation. So the bus assigned in our group is bus 7, and the following bus scheme that will be followed or considered in this project is breaker and 1/2, double breaker, double bus, and the ring bus, since it is in the 230 kilovolt range. Next is the bus configurations, cost, and reliability. So we considered the breaker and 1/2, double breaker, double bus, and the ring bus. Of the 3 bus configurations, double breaker, double bus is the most expensive with a cost of 1.75, while ring bus has a cost of 1.25. In terms of reliability, the ring bus has a reliability of 3, which is the highest among the 3 bus configurations, while double bus double breaker has the least reliability of 1. So another consideration to be made is based on the bus configuration's advantages and disadvantages. So here are the advantages and disadvantages of breaker and 1/2. So it has high reliability, flexible operation, can remove any breaker without causing a circuit outage, and can expand with ease without limits on the bay. However, the disadvantages are it requires large land area, it has a high cost, then 1.5 breakers are required per circuit, then each circuit should have its own potential source for relaying. Next is for the double breaker double bus. It is the most reliable, most flexible in operation, can remove any breaker without causing a circuit outage, and can expand with ease without limits on the bay. However, it also requires a large land area, it has a high cost, and 2 circuit breakers are required for each circuit. Next is the ring bus. So it has double feed to each circuit. It has no main buses, can expand to breaker and 1/2 configuration, economic design. However, the disadvantages are that each circuit must have its own potential source for relaying. And this is a more involved relay scheme since each breaker has to respond to faults onto 2 circuits. So, both configurations, all configurations provide respectable operation services that are suitable for usage in a designated bus. And most of the listed benefits are shared by both configurations. Both breaker and 1/2 and double breaker double bus have a relatively high cost, unlike the ring bus. Therefore, ring bus can be expanded to breaker and 1/2. And if we expand the ring bus to breaker and 1/2, the cost will still be the same as the ring bus. And in addition, it is much more reliable since breaker and 1/2 has a reliable score of 2. Therefore, the group's choice for the bus scheme is ring bus expanded to breaker and 1/2. Yeah. Then next. So we have here the simulation of the fault currents by using Power World. So in every bus number, the first 3 buses have a fault current of 35,000 and above. Next. And from bus 4 to bus 11 has an average of 2,227. And in bus 12, we have 33,000 of fault current. So bus 7 has an operated voltage level of 230 kilovolts with a fault current of 2,227.720. Therefore, the circuit breaker's short circuit current and interrupting capacity ratings need to be at least 22.3 kAIC. So we have here the equipment and specifications for assigned substation. So first is the ground. So the role of the ground is if there's a problem with the wiring system, electrical grounding acts as a backup path that offers an alternative path for the current to go back to the ground. Next is the surge arrestor or the surge protection device. So surge arresters are safety mechanisms that discharge or bypass surge current to minimize voltage on equipment. Next is the current transformer. So it generates a proportionate alternating current, AC, in its secondary to the AC current in its primary. Number 4, protective relay. So protective relays are components that are linked to circuit breakers to receive control directives for opening or closing and to instrument transformers to receive input signals. Multifunction power meter. So in order to process the real-time voltage and current samples from the user power source, a unique electrical circuit with a microcontroller is used. Next is the circuit breaker. So a circuit breaker is a type of electrical switch used to guard against short circuits, overloads, and overcurrent that could harm an electrical circuit. Next is the horizontal center break type isolator. So isolating the transformer, overhead lines, systems, or cables from the distribution network is the primary purpose of this device. So next, we have here our metering scheme or this single line diagram for bus 7. So we have the legends, the neutral current meter, line current meter, energy meter, real power meter, reactive power meter, power factor meter, residual voltage meter, phase voltage meter, frequency meter, circuit breaker, earthing switch, and the current transformer. So this is the single line diagram breaker and a half configuration applied to bus 7. Next is the protection scheme. So this is the protection scheme in single line diagram bus 7. So the legends here are directional overcurrent relay, directional ground fault relay, circuit breaker, earthing switch, and current transformer. So that's for our protection scheme.
So moving on to the parameters, rather the task 2, which is protection, we have here are or rather the SLD layout for the protection part. So here we can see in the illustration, it is an overcurrent protection works where the student choose their own values and settings. So depicted in the PowerPoint presentation is the assigned SLD layout for the students. And then it is necessary to adjust the relay currents value in order to control the circuit breakers 1 and 2. So the assigned faults are or can be found in circuit breaker 1, which is at the primary, and circuit breaker 2 at bus 5. So you can see here that bus 3 is connected to transformer 2. And then moving forward, we have here are the parameters and values for the protection. So you can see here the default settings for our source. We have 13.8 kilovolts, 350 MVA, and an impedance of 5. And moving forward to the transformers, we have 350 MVA and 150 MVA respectively for transformer 1 and 2. And then we have an alternating 13.8 kilovolts and 230 kilovolts, then 230 and 30.8. Then lastly, for the impedances of the transformers, we have X is equals to 8 and 9 for transformer 1 and 2. So for the transmission line 1, we have 1 plus J5 for the bus 2 to 3, and for bus 4 to 5 transmission line 2, we have an impedance of 3. Then we can see here, after conducting short circuit analysis, we have a fault current of 1,796 amperes for fault 1, and then for fault 2, we have 3,714 amperes. Then, based on the results in the ETAP, it's evident that the fault current rises as one moves farther away from the source and falls as one moves closer. Then moving forward, we can see here how the group performed the short circuit analysis using ETAP. So as I have said a while ago, we have 1,796 amperes for fault 1 for the fault current, and for fault 2, we have 3,714 amperes. Then we can see here the current discrimination. So for the current discrimination, it is the idea that a system fault currents weakens the farther it is from the source. So every segment in the beginning, there is a current-based protection placed. So the setting is higher from the maximum current generated by an upstream fault, but it is lower than the lowest short circuit caused by a problem within the monitored selection. And then moving forward, we can see here that the faults, the placement of the faults, which for the fault 1 scenario, which is near circuit breaker 2, and then for fault 2 is near circuit breaker 1. And then so 80% of the load currents will be calculated in the load currents at fault 1 and 2. Since there's regulation that we have encountered while searching for how do we compute for the current discrimination. And then the result was, it was 1,437 for fault 1, and then for fault 2 it is 2,971. And then moving forward, we have here the individual relay setting. So for the fault current 1 below bus 5 at circuit breaker 2, we have 1,700 amperes, which is rounded off to the process setting. Then for fault 2, we have 3,700 amperes. Then we can see below, beneath the table, we have here the definite time relay. So for the definite time relay, it is assigned that the time settings will be 2 seconds and 1.6 seconds respectively for every circuit breaker present. Then lastly, after applying all the parameters in the simulation, so here it is depicted the time current curve plot of the SLB. So here we can see that the time delay is 2 seconds. It has a CT ratio of 1,700:5. And then for relay 2, we have the CT ratio for 3,700:5. And then it has a time delay of 1.6 seconds. So the reason behind the CT ratio is 1,700 and 3,700 is because it is rounded off to the nearest setting. Then this is for the reference. That would be all. Thank you for listening.